Okay, so we are going to determine the x and y coordinates of the mass center of the homogeneous plate of uniform thickness t. And then I also threw this in here. Also state what the z coordinate would be conceptually. All right, so we have our three-dimensional plane here. We have an x-axis here, we have a y-axis right here, and then protruding out this way is our z-axis with thickness t. Now, it does seem tricky because the problem statement does give us a three-dimensional figure, but the conceptual part that I want you to see, which I wrote down here, is uniform thickness T. So because this plate, or whatever you want to call it, has uniform thickness T in the z direction, right? We don't really have to look at the z-axis per se when we're solving the x and y coordinates of our centroid. We could just think of it as our normal two-dimensional plane here. And apologies for the unneatness of my drawings. So this is going to be our figure in two dimensions, right? And then this is our equation, x equals ky squared. All right. So we can think about it just like that. Now, I'm going to erase this figure. Just wanted to get a little bit of a better visual of what exactly we are dealing with. So that should help us a little bit. Now we can think about this problem in two dimensions for, at least for the x and y coordinates of our centroid. All right, so I'm going to start off by solving for k, because k is an unknown multiplier that we should probably solve for, because we have our coordinate here at the very top. This is like our intersection of the bound, so our bound is meeting up at b comma h. So let's go ahead and solve for k. So solve for k. I'm just going to write that here. I know I stated that, but it's good that I write these things as well. All right, so let's suppose that x is equal to b and y is equal to h, right? That's one of our coordinates. We have our x coordinate b and our known y coordinate h. So those are our two known our one known coordinate. So we're going to just substitute that into our equation right here, our x equals ky squared. So let's go ahead and do that. So we're going to have, instead of x, it's going to be b, and then k, which is what we were solving for, h squared, because we replaced y with h. All right, so now if we solve for k, we divide both sides by h, we should be getting k equals bh squared. All right, I'm going to write this up here because we're going to need this in the near future. This is, sorry, not b, it's k equals bh squared. B over h squared. Okay. So that way I can erase all of this stuff. All right, great. So now let's go ahead and make a cross section. Now, should we make a cross section in the with respect to y or with respect to x? Now, what I mean by that is, should I make a cross section to where I have where I'm adding up all of these dx's on the bottom, or should I be adding up dy's on the top? Now, in all honesty, it really doesn't matter, but I would prefer doing it to where you keep this degree, because if you had to solve for y, let's say, you're going to end up with a square root solution, and then in your integration, you're going to have a square root that you're going to have to deal with. So I don't want to deal with that. Let's go ahead and make our cross sections with respect to the y. So I'm going to try to draw this as best as I can. I know that's not that great. Let's say our centroid is somewhere over here for this cross section. And then I'm going to, out here, I'm going to label this our thickness of this cross section as dy. Right? This is one of our cross sections of dy that we created just now. All right. So next step that I think is pretty vital and crucial for us to solving is what is our x bar and our y bar? What is our center of mass of this one cross section that we have here, and what is the center of mass of the y bar? So from this axis, from our coordinate, what is this guy right here? This is going to be our y bar, the distance up y to the center of mass of our one cross section. I'll denote that as y bar. And then from here, I'll draw a line out all the way here. And I'll kind of draw like a line down here, noting that this is the center of mass of our, in the x direction. All right, so let's actually do that over here. So what is our x bar? Let's solve for that one first. So x bar, this one is probably a little tricky. Now, if we look at this, if we look at just our one cross section, we can see that we're going a distance to this curve, x equals ky squared. So we can say that at any point x, this is at any point x, we're going that distance. And then what is this distance? Well, we know it's going to be this length halved, right? This whole length that we have made our cross section divided by 2. So what is this length? Well, we could say it is our length b. Okay, this is our length b all the way over here, minus our x. Yeah, so we have our length b from all the way over to this axis. This is b minus x, and that should give us this entire distance right here of this cross section. But we want to have that. So that's the idea. We want to say it's going to be our x plus half of this guy right here. So it's going to be x plus b minus x, and this is halved. All right. And we can actually simplify this. If you get a common denominator with the x, we can actually say this is simplified to b plus x over 2. So that's the equivalent way of writing this. But the idea I want you to see is like how can you find these coordinates of the x bar and the y bar? Okay, well now let's find y bar. Well, y bar is just simply going to be our y, because it's whatever y we're going up here. Now I can actually draw like some dashed lines denoting that this is where we're going to be going when we go up a distance y. It's actually going up to this whatever curve we have up here whenever we made our cross section. So that's our distance y, okay? So I'm going to circle these because we will be using these in our integration method over the next couple of steps here. Okay. Now what I want to do is solve for, I want to solve for dA. Well, what is dA? So dA is going to be simply, actually let me write this down here so that way I have some room. dA is simply just going to be our area of the cross section that we made. So dA, in other terms, is going to be our base that we made of our cross section, and we already said what that was. We stated that was b minus x. b minus x, right? This distance right here, I can actually label this distance, so that way we're familiar what this is. It's b minus x, and I guess I might as well get rid of this to clear up what we're stating here. So this distance right here is b minus x times dy. This is our thickness or our height of that cross section. So that's our area, or our dA is b minus x times dy. All right, great. So we do want to have one variable here. We have it with respect to y. So let's just replace x with our curve that we have here, because that's what we had our x. This is our b curve minus our curve x equals ky squared. So we can use x interchangeably with y here. So let's go ahead and do that. So we're going to have b minus, so ky squared, and I'm going to replace k with what we have solved over here earlier. So it's going to be b minus b over h squared times y squared. So I simply just replaced k with b over h squared, and then y squared is still going to be the same. Now, this is all going to be multiplied by dy. All right. So now let's go ahead and solve for the area of this entire thing. So our area is going to be the integral. Let's say we're going to add up all of these rectangles starting from 0 all the way up to h. So from 0 to h, those are going to be our bounds. It's going to be b minus b over h squared y squared times dy. So our area is taking the integral of dA, all of our little dAs. All right, let's go ahead and solve for this. Let's evaluate the integral. So we're going to have solution by minus b over h squared divided by 3 times y cubed. This is evaluated from 0 to h. Now, basically just plug in y equals h minus y equals 0. Now I'm going to skip the algebraic steps for the sake of time. So the solution is going to end up being 2/3 BH. And then it's going to be our integral of dA, or in other words, our total area. All right, so you can go ahead and do that on your own. Make sure that that is correct. Now we're going to continue and solve for our x and y coordinates of the centroid. All right, so let's go ahead. Let's do our x coordinate first. So I'm going to denote this as x sub c to denote that that is our x coordinate of the centroid. Now remember, it is the integral of all of our x bars and all of our dAs multiplied together, divided by the integral of all of our dAs, which we have already found. You should know that. Okay, so let's go ahead and plug everything that we have. We already know everything. We have our known values. We have our x bars, and we have our dAs right here. So let's go ahead and plug and chug. So our x bar is going to be b plus x, and this is going to be the integral b plus x over 2. This is x multiplied by our dA, which is b minus b over h squared times y squared times dy. So b minus b over h squared times y squared times dy. All right, now let me draw a line here separating our work. And all of this is divided by our integral of dA. I'm going to leave this as integral of dA for the time being. All right. We want to get everything in terms of y here. So remember, we replaced x with ky squared. So we're going to do that again. Replace x with our variables there. So, oh, and by the way, what are our bounds? Our bounds are also going to be from 0 to h because we're adding up, in this case, on the top, this is adding up all of our centroids with respect to all of our dAs. So we're adding up all of our centroids up this way. It's going to look something like that. So it's going to be from 0 to h. And we can actually take out the 1/2 if we want to, because the 1/2 is just a constant. So we can take, what I mean by this 1/2 is this 2 right here on the bottom. So we can take that out and put it as a 1/2 over here. Makes it a little bit simpler, just a tiny bit. All right. So b plus, and we're going to replace x with ky squared. So k we said to be b over h squared times y squared. Times y squared. All right. And this is multiplied by, I'm going to separate that there. B minus b over h squared times y squared times dy over all of our integrals of dA. Okay, so we can FOIL this out, and we should notice that these are factors of a minus and a plus of the same things, right? We have b plus b over h squared times y squared. This is b minus b over h squared times y squared. So if we factor this out, we're going to have, or sorry, not factor, but if we FOIL, rather, we're going to have this. So it should end up being, now you can go ahead and FOIL this out. I assume you should know how to FOIL. It's going to simplify to b squared minus b squared y fourth over h fourth times dy, right? Because we factored in, we FOILed in a b here, this gives us b squared, then we FOIL b times this guy, which is negative b squared over h squared times y squared, and then we FOIL in this guy, so it's going to be positive b squared y squared over h squared. So those two terms actually cancel out, and then we're left with b squared times y to the fourth over h to the fourth. And all of this is divided by, you guessed it, our integral of dA. Okay, so I believe we should be able to evaluate this integral now. We've simplified it pretty good now. Let's go ahead and do that. So it's going to be 1/2 times b squared times y minus b squared times y to the 5th, right? Add one exponent, divided by 5 over h to the 4th. And all of these are added from 0 to h. All over the integral of dA. Okay. So let's go ahead and evaluate here. So we're going to have 1/2 multiplied. I'm going to put brackets here actually. So it's going to be b squared times h minus b squared times h to the 5th. And now h to the 5th over h to the 4th. Now this does look like h times 4 rather than h to the 4th. So let me make sure that this is an exponent. So it's h to the 5th over h to the 4th, which should just simplify to h over 5. And then evaluating at 0, we should have minus, if we plug in y equals 0 here, it's going to be 0, and then y equals 0 is 0. So we're going to have a net result of 0 right there. And this is all divided by our dAs. Okay, so let's simplify the numerator a little bit because we have some like terms we can combine here. So we have 1/2. Now, if we get a common denominator of 1, so this is, pretend this is 1 in front of here, common denominator of 5 over 5 minus 1 over 5, it should give us 4/5 b squared times h. And we can go ahead and substitute what our integral of dA was, which we set to be 2/3 bh. So let's go ahead and do that. So it's going to be divided by 2/3 bh. All right, let's go ahead and simplify this out. Now if we get rid of some of these terms, we have a term we can cancel out here. 2/3, we can actually get rid of 2 here. And then we have 12 over 5 over, actually, sorry, no. This should be 3 over 5, right? Okay, let's simplify this actually. So this should be 2/5. And then we can cancel out the 2's here. And then 3, it should simplify to 3/5 b. 3/5 b. So that is our x-coordinate of the centroid. Now let's solve for our y-coordinate of the centroid. So let's go ahead, I'm going to write it down here. So our y-coordinate is the integral of all of our y bars times all of our dAs divided by the integral of our dAs. All right, so the only thing we need to plug here is what is our y bar and what is our dAs. So our y bar, remember we said is just y. We determined that, just going up distance y to the center of our cross section. And our dA is b minus b over h squared times y squared times dy. All right, so let's go ahead and plug and chug. So we said y times b minus b over h squared times y squared, all of this multiplied by dy. And these should be added from 0 to h again because we're adding up all of our y coordinates of the centroid because we're doing rectangular cross sections with respect to the x-axis. So we're going up a distance of all of our cross sections of our rectangles from 0 to h. So that's why we have limit 0 to h there, divided by all of our dAs. Now we know what this is. We've already solved for that, so we can plug that in later. Now if we go ahead and solve for this integral, basically you just want to FOIL out y into these two terms right here. And I'm just going to go ahead and skip a step. So I'm not going to FOIL that in. I'm just going to go ahead and evaluate the integral just to save some time here. So we're going to have y squared over 2 times b minus b y to the 4th over 4 h squared, and all of these we're summing from y equals 0 to y equals h over the integral of our dA. Okay. And now we evaluate this. It's going to be h squared b over 2 minus h to the 4th. So h to the 4th over h to the 2 should simplify to h squared times b over 4 divided by our integral of dA. Okay, so we see that we have common terms right here, so let's go ahead and do that. So this should simplify to h squared times b over 4 divided by, and now we're going to substitute dA, which we solved for earlier. Remember, it's 2/3 BH. And if we simplify this, just multiply, well, you can do division, or you can multiply by the reciprocal here. And if you do that, we should end up getting 3/8 h to being our y coordinate of the center of mass. All right, so that is great. Now we've done all of the hard parts. Now let's state conceptually what the z-coordinate would be of this center of mass. So just to get an idea, I'm going to erase what we've done here just to kind of get us to see something here. So the z-coordinate, what would that be? Well, you can just look at this, just look at the z-axis. Look at that axis normal. What I mean by that is just look at the axis like this. That way you can ignore this curve right here that we've been dealing with for our centroid. And why is it safe for us to say that we can ignore that and we can just look at our thickness d like this, our thickness t. Pretend this is our thickness t. Well, because it's a uniform thickness. So because it's a uniform thickness, if we look at our axis normal, let's say I'm looking at my axis normal like this, in this direction, right? If I'm looking this way, I see that T, or this little guy, is actually just going to be a rectangle. Now it doesn't look like a rectangle because of my drawing skills, my poor drawing skills, but this is actually going to be a rectangle if you look at it in the z-axis, just normal to the z-axis. So it is safe for us to assume that the z-coordinate is just going to be half of that, because obviously the centroid of a rectangle is going to be half of whatever that distance is. So our z-coordinate of the centroid, or the center of mass, is just going to be t divided by 2. So to recap, now let me go ahead, I'm going to go ahead and write all of this up here. So as a recap, the coordinates of our centroid, I should go ahead and erase all of this. I'll write it up here. I'll just erase that k that we solved for. So our coordinates of our x, y, and c, to recap as a summary. So xc, comma, yc, comma, z sub c is going to be, now we said our xc is 3/5 b. I hope I have enough room to do this. 3/5 b, now that doesn't look too promising of a 5 right there. Let's draw a better 5. 3/5 b, comma, 3/5 a, or sorry, 3/8 times h. We go back down here. 3/8 h is our y coordinate, and our z coordinate we just said was t over 2. So there you have it. That is our centroid, or our center of mass, in our component form right here. Thank you so much for watching. I hope the video helped you learn something today. And if you have any questions, feel free to leave that in the comment section below. And I will hope to see you in another video.